Today I'm going to show you guys how to prepare for an exam using an equation sheet. This is my favorite strategy because this thing is going to be in the exam with you. So you need to build your foundation of knowledge and your plan for the test off of this document. Here is an example one for modern physics, and I've posted some videos about equation sheet study guides before. You kind of know the plan over here. But for those of you that don't, and also since I have a slightly different strategy today, I have a legend over here, which is different colors for different notes. So over here I got notes in white. Whatever I want to say about the equation, I'm going to just write in white, or maybe I'll keep it themed over here. We got relativity in blue. I think of relativity, I don't know, as blue because you look up at the sky, you imagine relativistic things going super fast, and the sky is blue. Quantum mechanics is pretty scary. I have that in red. Atomic physics, I don't know. I think of this pink color as pretty unique. You don't really see this around in nature. Like, people don't really wear this color often. So, and I think of atomic physics as unique physics. I don't know. We're going to write that in pink. Constants are in green. Green is good. Constants, normally we don't need to remember anything. It's just a constant. It's given to us. We might have to know the name, whatever. And then I have two more miscellaneous colors. I don't know. Maybe I can take extra notes with this. But I'll reserve the notes for white. Or actually, if I have important notes, I might keep it in the same color as the subject. And the modern physics curriculum normally can be broken down into these three big topics here. Quantum physics, quantum mechanics. Atomic physics, kind of the later chapters, and relativity, the first big chapter. So my goal today is write a little bit about each equation. And here is the equation sheet. We're going to start from here, go down, and then once we finish, we're going to go with this column and this column. And yeah, whatever I don't know, maybe I'll put it in like a different color. Maybe one of the miscellaneous colors. Maybe this will be the I don't know color. And then we'll go back to it. Maybe we can do a second part to this video. So let's zoom in. The quality of this is fairly bad, so I'm going to just write over this with my pencil. This is KB. I think what this means is Boltzmann with one, maybe two ends. Boltzmann's constant, const. So this is green because it is a constant. I'll circle that in green like that. What do we have here? Let's just take a look at 1.38 times 10 to the minus 23. This is joule per Kelvin, I believe. Joules per Kelvin. All right. So yeah, I'm not sure what else to say about that. It is a constant. Now we have this here. This looks like Ke. I think this is Coulomb's constant. 8.987 times 10 to the 9 Newton meters squared per coulombs squared. I'm not sure why this is here. This is actually ENM. I'm gonna just keep it as that, and maybe I'll do Coulomb over here. All right, we got a constant over here, which I will overline in white again. I think this is R subscript H equals 1.097 times 10 to the 7. The units are meters to the minus 1. I'm actually not sure what this is, so I'm going to put some question marks here. And, you know, I'll write here, check summaries. Check summaries. Because I did the 7-minute summaries, this should be helpful. Nice. So looking good so far. Next equation here is 1 FM. I think this means femtometer equals 10 to the minus 15 meters. This is just a constant or unit conversion. I'm right here. Unit conversion. If you want to go from femtometers to meters, you can use this equation. Not too much to talk about there. Now we have 1. I think this is Ci. I think this stands for Curie, after Marie Curie, but I'm not too sure. 10 to the 10, 3.7 times 10 to the 10. This is decays per second. So again, we can put this in green because it is just a constant, like it is a conversion between units of Curie to units of decay per second. Let me actually check on my phone. What is 1 CI or 3.7 times 10 to the 10 decays per second. Just typing that into ChatGPT, we'll see what it says. 1 Curie. So this here stands for 1 Curie. Is a unit of radioactivity originally defined as the activity of 1 gram of radium-226. It is equal to 3.7 times 10 to the 10 decays per second, or becquerel BQ in SI units. So this actually is BQ. Becquerel, another, I don't know if I'm saying that right, another unit for decay. Cool. So we can talk about that a bit more. It's an interesting kind of conversion, and you can imagine some interesting problems related to decays per second. But anyway, at the end of the day, it is literally just a conversion. Meters to centimeters, pounds to kilograms, Celsius to Fahrenheit, whatever. Not too much equation-wise to talk about. Here we have an M. I'm not sure what this means over here, what this little symbol is. As you can see, my equation sheet is kind of low quality. Well, we got an equal sign 1.674 times 10 to the negative, what does this mean? What is this saying? 27 kilograms? Let me actually search this up as well. What is 1.674 times 10 to the minus, I'll do 27 kilograms. And if it's important, mass of a neutron. Okay. So this little n, this little symbol over here is a n, mass of neutron. Maybe I should write that in green. Neutron, as it is just a constant. Nice. So now we know that there should be some other similar ones. Over here I can actually see this one is mass of electron. Electron mass. This is 9.1 times 10 to the negative 31 kilograms. So it is lighter than a neutron. The electron is the lightest out of the neutron and proton. And I'll also write this in green, electron. And I will put a green constant bar around it. Let's go back to this H over here. We got H is equal to 6.626 times 10 to the negative 34, I believe. This is joule seconds. So this is joule and this is seconds. And I think this H is Planck constant. So another constant, we're going to go like this, and just confirm that this is to the minus 34. Let me actually check that. Planck constant in joule seconds. I'm just typing this into ChatGPT. It should give it to me 6.626 times 10 to the negative 34 joule times second. It also gives me this equation. ChatGPT, very helpful for this. E equals HF, which is important, but since we're just looking at the equation sheet, I'm not going to write that there. It might come up later. So we got a bunch of constants here on this first column. We're going to zoom through and we see a familiar one here. C is 3.0 times 10 to the 8 meters per second. And this here is speed of light in meters per second. Another constant. Very cool. And it's good to know what the units here mean, meters and seconds, because then you can convert and kind of solve for some unknowns. We got another mass over here. Mass proton, in this case, 1.673 times 10 to the negative 27 kilograms. I remember its mass of the proton because it's very similar to the mass of the neutron, 1.674, 1.673. So I'm going to just write here proton mass. Again, in green, we are not done with the constants. Then we're going down here. This looks to me like an epsilon naught equals 8 point. What is this symbol? I think it's 854 times 10 to the minus 12. This is Coulomb squared divided by Newton meters squared. This thing is actually Coulomb's constant, 4 pi epsilon naught. So if you plug these units into here and you do pi, you should get Coulomb's constant, which we saw was actually at the top over here, which I didn't circle in green. We can actually circle this. I just wrote E and M over there. Coulomb's constant. Okay, maybe not too useful since it's a modern physics course. We didn't do too much E and M. But let me erase this. And here, this symbol I think is called permittivity. Let me check permittivity constant. It could be that, or it could be permeability. No, this one's permittivity. So here they give it in Coulomb squared per Newton meters. By the way, it's important to know that we're dividing by this entire Newton meters thing. This is on the bottom, and C squared is on the top. There's another way of writing it with farads per meter, but whoops, let me just complete this. Permittivity of free space. Another green box for the constants. Now we get to something that I'm a little bit unsure of. I remember seeing something like this in the 7-minute summaries, but we got basically here a Q equals, then we got M, let me write that M a little better, M, a symbol here, it maybe looks like XYZ, minus another M minus another M. I'm not sure what symbols those are. Then we have 931.5. And then it says in mega electron volts per U. So I'm going to put this in this little miscellaneous color. And I'll just do like, I don't know here. Atomic chapter, maybe. I'm going to just check that later. Not sure what it is. Now we get to the equations that I know are from relativity. So I'm going to circle all of these. And I think these are called the Lorentz transformation equations. Nice. So what we have here is in the direction of motion, we have the direction of motion, which is x, right? X over here. You subtract vt. V is the speed that you're going at. Gamma over here is the relativistic factor. And you have the Lorentz transformation equation for the x direction, which is the direction of motion. In the y direction, you do not have any motion, so the y direction does not change. Y prime equals y. And we're not moving in the z direction, so z prime equals z. There is also a time transformation equation. We have a gamma factor out here. We got these whole brackets. Time, and we subtract this extra factor, which is the velocity we're traveling at, divided by c squared, times the distance we have traveled. So Lorentz transformation equations, the relativity section, we're writing it in blue. I'm not going to talk about this too much. It's good to do some problems, and then you'll get a kind of a hang of these equations. But they're here if you need them. So cool. We finished it. The first section, I have 2 unknowns. I have 1 equation on relativity, and everything else is constants. All right, let's keep moving. And we got another constant. This here is 1 electron volt, a unit of energy, equals 1.6 times 10 to the minus 19 joules. This is joules, another unit of energy. Just a conversion factor between 2 different types of energy, electron volts and joules. It's like converting from kilograms to pounds. Pretty nice. Now we have the electron charge, which is negative 1.6 times 10 to the negative 19 coulombs. Electron charge. Nice. Maybe here I should write energy. Energy. Nice. Electron charge, you could do with that what you wish. I don't think we've seen it in this section. It's the modern physics, so maybe there's some kind of problems that you'll do, like an electron is traveling at some velocity. Use the electron mass and the electron charge to do something. So they give you those things there. Now we got an equation from quantum. So I'm going to put this with a little box underneath. This is the Wien's law. I did a video on this. Basically, it tells you the peak, I think this here says peak lambda at a specific temperature. You multiply those two together, and this gives you a constant, which here has units of meters times Kelvin. So if you remember that plot, you plot here lambda and you plot here intensity. If you glow stuff up, they produce some kind of distributions like this. And if you have like different temperatures, the peak light that is emitted will be different. So here's the peak here, there's another peak here, there's another peak here, there's another peak here. All of these are at different temperatures. Maybe this is 1 Kelvin, 2 Kelvin, 3 Kelvin, whatever. So this equation here, if you know the temperature of your object and you know the peak wavelength, you can multiply those two together and they should give you this constant over here. But if you don't have one of these, let's say you're told the peak wavelength of your object and they ask you what is the temperature this object is at, you can use this equation here, divide some stuff, some algebra, and isolate for the unknown. So this is Wien's law, and it is colored in red because it is from the first quantum physics chapter, chapter 40. Nice. Let's move back. We got another unit conversion. 1 U is equal to 1.66 times 10 to the minus 27 kilograms. So this is green here. I'm going to put it green, but I'm also going to do atomic unit here in pink because I remember this U comes from the atomic chapter. It's a way of converting between U is some kind of mass, I don't know, the atomic mass or something. Basically the same thing as the energy conversion or pounds to kilograms. It's just the atomic physicists are like, hey guys, we're tired of using kilograms because we always have things that are super, super small in kilogram weight. So we're going to convert it to this unit U over here, which is helpful. So if you see a U anywhere and it says atomic mass, atomic unit, anything like that, you can use this equation to convert between kilograms and atomic units, or whatever this U is. It might be like atomic something, I don't know. Whatever the name is, search it up, figure it out. You guys got this. Next equation here, we got frequency times lambda wavelength equals c, the speed of light. So this I will say is relativity. But it is general, like kind of wave behavior. You guys have seen this in the optics section. If you have seen, if you've checked out my optics videos. So I will just write here, light. Here this is frequency. And here this is wave length. Maybe it's getting a little messy here. Maybe I should have written that in a different color. We're going to keep going. Now here we got something that is from the quantum chapter, I would say. This is the, my bad. This is the de Broglie wave length. So you got a lambda here. This is the de Broglie wavelength. You have h, which is a constant. The h constant is actually given to you right here. So if you want that h, you can take it and make sure you follow the units. It is joule seconds. Over here you have p, which is momentum. So if you have an object with specific momentum, you can plug it into this equation and find what wavelength it has. This is important because in quantum mechanics, things can be both particles and waves, or waves, particles, or waves, particles and or waves, whatever. So sometimes they have a wavelength, which normally you don't talk about. Like in classical mechanics, they never tell you, we have a basketball with wavelength 5 meters. You know, they just tell you the basketball has a position, a velocity, an acceleration, whatever. But de Broglie found out that waves can have momentum and particles can have wavelength. So use this equation, and you can use this equation coupled with the one right above it, this one right here, to find the frequency of an object. Super interesting. All right, let's move on. We got here E. I'm assuming E is energy. Here we have H bar, which is a symbol we have not seen yet. Then we have 2I, I believe. Is this I? Then we have J over here plus 1. So I'm going to put this in red because this is quantum mechanics. I think this means energy. But I'm going to circle it with this, I don't know, color because I'm not too sure what these J things mean. And I also don't know if there's an I over here or if my equation sheet is kind of low quality and I'm kind of mixing up I for J or something like this. But I know that this is H bar over here, which is the reduced Planck constant. This equals H divided by 2 pi, if I'm not mistaken. Let me actually search this up. H bar versus H in ChatGPT. So they tell me H is Planck's constant, and H bar is the reduced Planck's constant, which is just H divided by 2 pi. Same units, is just getting reduced by a little bit, which is the 2 pi factor over there. So I don't know what this is. I'm going to just put a little I don't know there so I can go back and make sure I know what it is. Now we got another relativity equation, gamma factor. Take a look at this. We have gamma over here, Greek letter. It equals 1 minus v squared divided by c squared. And this entire thing is to the power of negative root. So what a negative root means is just take everything in the brackets and put it to the denominator. So in this x, you put everything inside these brackets. This is x. So the gamma factor is introduced in relativity. It is useful for time dilation, length contraction, all those things. So take a look at that gamma factor. We can do some problems related to that later. I think I did one problem related to length contraction, so take a look at this video. Here we got, I think, another relativity. I know this is energy for sure because I've seen this equation before. I just don't know about it too much. So we have E squared here equals P, which is normally momentum, squared, C, which is the speed of light, squared, plus brackets. Everything inside the brackets is squared. mc squared, which is mass times the speed of light squared. But I'm going to put an I don't know here because I haven't done any problems with this, so I just want to refresh this. But I do know it's in the relativity section. So I'm putting it in blue, which is the relativity. Here we have something else that I think is also relativity. Let's put it in relativity like this. The reason I'm saying that is because I see this factor over here. Let me just draw it in white. I see this factor over here, which is 1 minus ux, which is velocity in the x direction, times v, which I think is velocity of the frame of reference. All of that is divided by c squared. So this to me looks kind of similar to what's happening in the gamma equation. And we also have, so this is a division symbol. And here we have the numerator, here we have the denominator. So we have some fraction here. And this entire equation gives us u prime x, which is the velocity in the x direction in the moving reference frame. This little prime means the moving reference frame. It depends on your perspective. Sometimes it might be the non-moving reference frame, whatever. But I do know that we are talking about relativity type stuff. So we have here ux, velocity in the x direction, minus v. So we have v ux, we have ux prime. Take a look at the Lorentz equations again. Remember that we did the Lorentz equations over here. So you can see this x minus vt gamma. I'm sure that something similar to that is going on here, but I'm not too sure. I haven't used this equation, so I will do an I don't know so that I can do a problem with this and I can feel comfortable with this equation. We're going to move through though. I want to make this video fairly solid in length. I have an E here, which normally I think stands for energy, but I don't know what the symbol is. It looks like a lowercase b, but I could be mistaken, and the equation doesn't jump out at me right away, so I don't want to say it's b. So we have here equal sign, big brackets, and then we have a z, m, I think this looks like a p, plus n, m, I'm not sure what this is. This looks like a square, minus lowercase m, all of the m's are lowercase, and this looks like a capital A. And here we have 931.5, which instantly kind of reminds me of something we've seen. Take a look at this. I'm going to use miscellaneous color 2. 931 in mega electron volts, and then here we have these M's. This looks super similar to this equation here. You see this 931? Actually, there should be a decimal point over here. 931.5. Here we have 931.5. Right underneath the equation, it gives us the units in mega electron volts per lowercase u. Remember, mega electron volts or electron volts were discussed over here. Electron volts conversion to joules. And we also have this U over here, U conversion to kilograms. So these units are basically energy divided by kilograms, right? Energy divided by kilograms. Energy density, I don't know, something like that. We have 3 terms over here being subtracted by one another, 3 terms here. In this case, we have a plus sign and a minus sign here. In this case, we have a minus sign and a minus sign. But the same 931, 931. Here we have energy and here we have Q. So I can again say this is kind of from the atomic physics chapter. Let me put this in, wait, atomic physics was in pink. So I'm going to do atomic physics here because now I'm kind of fairly confident it's atomic physics. We're talking about electron volts. We're talking about this little U. So put this in pink. And I'm also going to do like IDK over here. Do a problem related to this. The atomic physics, I just did a quick 7-minute summary recently, so I haven't really seen any problems related to that. Okay, now we are back to quantum mechanics. This is the Heisenberg uncertainty. Whoops, I kind of wrote that a little bad. Uncertainty principle like that. So what it looks like is delta x times delta p subscript x. So delta means difference in and x means position. Delta, difference in momentum, and momentum subscript x means momentum in the x direction. So the difference or the uncertainty in the position multiplied by the uncertainty in the momentum must be greater than or equal to h bar divided by 2. We already know that h bar is related to quantum mechanics. It equals the h divided by 2 pi. And this here tells us uncertainty in position and momentum. So I'm going to leave that here. I'm going to erase this to keep it a bit more clean. But yeah, I also am going to do like a little I don't know here because I haven't done any problems related to this. So I just want to practice this before going into the exam. Looks good. Now we have this longer equation here, which looks like an E. Not sure what this symbol is. Looks like a little square. I think here we have a minus sign, and here we have a big bracket. Big bracket. What's inside the brackets is KE. Is this a KE, I think? KE is the Coulomb constant, which we have seen up here. So Coulomb constant, here's the value and the units. I know that the font looks kind of crazy. Sorry about that. But this looks like it's useful here because we have an E squared. This looks like the charge of the electron, which is actually given to us right here. Charge of the electron, the value, and the units. And at the bottom we have this 2, and this looks like a lowercase a, which I don't like writing like this. I normally write my a's like this, and subscript 0. So is there an a subscript 0? There is. A subscript 0 equals 0.052 nanometers. So I'm going to just put this in green since we've looked at it. This looks like a length, some kind of length. But I'm going to put an I don't know because I don't know what it is exactly. I just know that it's a constant, right? That's how they write constants. But I do know that I have its value here. This is its value, and I have its units, its nanometers. And I know it's a length because nanometers is a length. I just put a I don't know because I can't remember where I've seen this before. So in the equation sheet, we are given this, we are given this, we are given this. We know what 2 is. So automatically this little first thing is very good. This z over here, which follows, everything here is being multiplied by the brackets. Z squared over n squared. Now, I haven't seen anything related to Z yet. No, I have seen nothing related to Z. So Z, I think I should put like a little question mark here. Now, to continue, I think this is another equal sign over here. This gives us 13.6 divided by n squared. Notice the n squared here is similar to the n squared here. Just a little observation. And then here we have a z squared. I guess the z squared is also similar. And then here we have electron volts. So it seems to me, take a look at this. This and this z squared divided by n squared, this is just shifted over. We have the same thing here, z squared divided by n squared. And now we have this new thing, 13.6, and the electron volts. So my argument is these two things together, 13.6 electron volts, is exactly what's in the brackets here, because there's an equality here, minus sign, equality here, minus sign, and the equations look identical. So I know this is an energy, and my guess is that this is a lowercase n over here because we have n, which tells us n can be an integer. N equals 1, 2, 3. So what I think this is energy levels of a hydrogen atom or something related to this, something related to quantum mechanics. So I'm going to put a quantum mechanics color bar around this. I will do, I don't know, energy levels, question mark. And maybe I'll put a little n over here since I kind of am just guessing this is an n. But still, I don't know for sure. So I'm going to just keep this little color here. Maybe this color isn't the best for the I don't know. I want the I don't know color to jump out at me. But anyway, it looks like we're very, very close to done 2/3 of this. Let's finish off with this guy here. And actually, look at this. This guy, we already know. We've seen it before. It's 1U equals blah, 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 some number, kilograms. This is the atomic units that we have seen right up here. So this guy we already know. Actually, since we already know it, we don't really need to like bother ourselves with it. So I'm gonna just erase it, actually. We already know it. All right, let's move through. Let's take a look at our progress so far. It looks pretty nice, right? So we have mostly constants. All the green stuff, you don't have to learn anything about it. It's just given to you. It's constants. Maybe you have to know what it is, the name, but I gave you guys the name here. So you can just hop on ChatGPT, search up what does 1 Curie unit mean. Curie equals 1 Curie equals decays per second. Ask ChatGPT, read about that for a second. But anything in green, you don't really have to worry about. We got 3 or 4, maybe 5 equations related to relativity. We got 5 or so equations related to quantum. And now we are on to the last column. So let me erase this, finish off with the last column. Off the bat, I know that this is relativity. Let me change my thing over here. This is relativity. Relativistic momentum. So I know that's the case because here I have P, which is a vector, equals, I see a gamma, which is what is like jumping out at me and telling me this is relativity, because gamma is the main thing that you worry about in relativity. We have M, which is the mass of the object, and we have U, which is the velocity of the object. So an object with mass M and velocity U, you can plug in its relativistic gamma factor and you can get its relativistic momentum. So whenever that's helpful to you, you're doing a relativity problem and they're asking you for momentum, boom, you can use this. We have another relativity problem or relativity equation, which is kinetic energy, relativistic kinetic energy. So capital K is energy. We have a gamma mc squared minus mc squared. Remember that kinetic energy is half mv squared. So if you want to find relativistic kinetic energy, you replace this v for a c, the speed of light, and you have gamma over here, which you have been given before over here. Take a look. Gamma actually has a c in there, and it has v squared in there, which is the velocity of the object. So whatever velocity your object has, it goes into this gamma. You have an mc squared factor and then the mc squared factor here. This, I think, is the rest mass energy. I'm not sure, you can read about that a little bit more, but actually, since I am unsure, I'm going to put a little I don't know here and I don't know here because I haven't done problems with these. I just know where they're coming from. So off the bat, I can kind of give a bit of info, but I would like to do a problem related to these so I can see what the tricks are, you know? Now we got an F equals, we got an KE E squared over 2AO, which automatically, this little factor here jumps out at me because we saw it right over here. KE E squared, there's a KE over here, and then here's the 2A subscript O, and we found the 2A subscript O here. Same kind of factor here, except we have an H over here, which is the Planck constant, I suppose. Now we have big brackets over here. We have 1 over N squared, I'm not sure what this is, minus 1 over, again, N squared. And this to me looks like an I, and this to me looks like an F. So I think this means initial, and this here means final. I should actually work with this font size because it's less like blocky and bubbly. So I'm going to put here atomic physics. Actually, let me put this, let me keep the original font size so I don't mess anything up. Energy. So what I remember here is we have some kind of like energy levels like this. So maybe this equals N equals 1, 2, 3, 4, 5, 6. And then you have like an element or electron dropping down into these. You guys remember seeing these graphs from here to here? So I think this is what Ni and NF means here. But still, I'm not sure. I haven't seen this before. I'm just kind of guessing what section it is. I'm guessing that it is from the atomic section, but I don't know. I would like to do a problem. Now we have, again, something related to relativity. Relativistic energy, perhaps. We've actually seen this before. This is E is equal to gamma mc squared. Now just take a look at this. Gamma mc squared. Here's a gamma mc squared. And here is a gamma mc squared. So you can replace this whole thing with E, because that's what this equation is telling you, minus mc squared. So this is kind of telling you some new information. Energy minus this little mc squared gives you kinetic energy. Maybe if you plus this on this side, you get energy equals kinetic energy plus this term. I'm not sure. I'm just kind of doing things here. I'm also going to put an I don't know here because I haven't seen this equation. I haven't worked with it. I just know that it is relativistic, like it's from the relativity chapter, and it is related to energy. Ooh, let's take a look at this. I think this is quantum mechanics. Let's close this circle off here. So this gives me kinetic energy max is equal to H, Planck's constant, F, frequency, minus, and this is phi, the work function. And I know this is the photoelectric effect. Take a look at this, some classic problems related to that. I will do some problems, but since I haven't on this channel, I will also put an I don't know. Let's move on. Again, we see the same kind of factor here. This KE, E squared, 2A naught. And here we have a minus sign. And remember, we've seen this several times here. We saw it very recently, just up here, right? If we remove this little H in the bottom. And we saw it over here, the same factor. And from this equation, we actually saw that that entire thing equals 13.6 electron volts. So ask ChatGPT what is 13.6 electron volts. It's a very, very commonly used number. I think it's some super common energy value. Like, I think it is the energy it takes to remove an electron from a hydrogen atom. So a hydrogen atom is the nucleus with one electron over here. They're connected by some, this is hydrogen. They're connected by some energy. And then if you want to push this electron so that it escapes this little nucleus, you get hydrogen plus, because there's no, it's now positively charged because you got rid of this electron. And I think the energy is 13.6 electron volts. This is how much energy it takes to separate these guys. So it is how much energy is between these guys as well. I'm not sure, take a look at that, but I just can see that this factor here is appearing everywhere. So other than that, we see that the equation is E, and I know this is an N over here because I see an N over here. And I know from before that N could be some of these integers here. So maybe I'll put that just for personal knowledge. And I will also put pink over here. Maybe I'll also put a little red, but I'll also put an I don't know. I'm putting a red because normally you start off learning this equation in the quantum mechanics section, but then you apply it in atomic physics. So that's why I'm putting multiple colors here. I'm still putting an I don't know because I haven't used this equation before, but I've seen it multiple times in this equation sheet, so I'm kind of getting more comfortable with it. We're almost done. Let's finalize with lambda prime minus lambda subscript 0 equals h Planck's constant divided by mc. All of this is being multiplied by 1 minus cosine theta. So I know off the top that this is in the quantum physics section, and it is specifically the Compton effect. Compton shift equation. So I haven't done a problem related to this, but I remember clearly in the 7-minute summary, I saw this equation and I saw it was in the Compton effect section. So it is here. I'm going to go back, do a couple problems related to it, see how difficult that is to learn. We got something here that I haven't seen much before, but we're going to take a look at it. So we have capital R equals these absolute value brackets. Then we have a time derivative, d dt of n. I don't know what n is. I haven't seen it before. All of that looks like equals. This is an equal sign. Here we have a capital R subscript 0, e, which is the Euler number, to the power of minus lambda. And I'm not sure what this is here, but what I can tell you guys is I know this is in the atomic physics section because this thing over here I know is a decay rate parameter. In every decay equation, you see something like this. So I don't know exactly what this is, but I know it is related to decay because I've just seen this equation. If you plot this, if you plot y is equal to e to the minus x, you will see it literally looks like this. Plot here, plot here. If I plot it like this, it decays like that. So this equation is very, very commonly used when you're talking about decaying processes like radiation or anything along those lines, like reduction of a population of a species of rabbits. I have no idea. Something like this, you will see it often, so it just jumps out at me instantly. But I don't know what it is, and I don't want to spend too much time just staring at it blankly. So I'm going to keep going. I have t subscript 1 over 2 is equal to 0.693 over lambda. I gotta be honest with you guys, I have no idea what this is. So I've never seen it before, I don't think. And I'm gonna put big stars around this because something that I don't even know what section it's coming from, it is pretty elusive, and I don't want to be in the exam being asked to use this equation without knowing what it is. So I don't know, but maybe just off the top of my head, what I'm thinking is I have a lambda here, I have a t here. Maybe this means temperature, and maybe lambda means wavelength, right? We've seen this fairly commonly. If I multiply lambda here, I got an equation lambda times t equals some number. This number here, it doesn't have any units, so it is unitless, but this form of the equation, lambda times t equals some constant, I actually have seen here. I've done a video on it, Wien's law. You see here I have a lambda, don't worry about the peak, times temperature equals some number, but this number has units. It has units of meters Kelvin. So I'm not sure what's going on here. I also don't know why there's a 1/2 in the denominator here. Or not the denominator, but the subscript of the t. But I don't know. I'm going to just leave it at that. So we'll zoom through. And we see here n actually is the same n that we see here. So we have n is equal to n subscript 0 e to the power of negative lambda. I think this is t. I'm not too sure. But again, atomic physics, and I can tell you this here is decay rate. So boom. However, orange color, I don't know. star. Do a problem on this. But you can see the decay rate parameter is also there. And if you want, you can actually take this function. Let me use a laser pointer here. You could take this function, which I'm telling you is a function of time. I put a question mark because I don't know if this symbol is time. It could be a different symbol. I'm assuming it's time because if you take this equation here, n, and you replace it here, you basically take this whole thing and you put a dt in front of it. Now you have to take a derivative of this and this. This is a constant, so you can move it out, right? And this here, the derivative of this just brings down a minus lambda, I think, and it gives us the same thing. So I think there's a minus lambda over here, and I think this over here, n over minus lambda, gives you this r over 0. I'm not too sure. I'm kind of just eyeballing it over here. Also, this thing now looks a bit similar. I think this is half-life, right? Time. This might be time. This might be half-life time equals some kind of percentage over lambda, which is meters. Maybe it's not half-life, because if this is unitless and this has units of meters, this would have units of meters to the -1. I'm not sure. So we're just going to leave it as that, and we're going to leave this equation like that as well. So we got 2 more equations and then we're done. Let's take a look at it. We got E is equal to open bracket, close bracket. Inside the brackets is V plus 1/2. Haven't seen that before. We're multiplying this whole thing by H divided by 2 pi, which actually this whole thing we can rewrite as the reduced Planck's constant because that's how it's defined. But we'll leave it as that for now. Then we have a square root, and here we have a k over mu. So I don't know. I'm going to put a red box here like this. Quantum. But I have never seen this before. I'm not too sure what it means. Maybe I can guess, but I don't want to guess right now. I just want to put a quantum thing there because I see H. H is the Planck's constant. It normally appears in quantum sections. Maybe atomic sections as well, but who knows? We're going to take a look at that equation, see where it comes from. We're going to study it. And then this last thing is again quantum, and it is very similar to the Heisenberg uncertainty principle because it is the Heisenberg uncertainty principle. There are 2 really popular ones. The first one is with respect to position and momentum. The more you know a quantum particle's position, the less you're sure of its momentum. The more you know its momentum, the less you're sure of its position. Here, the more you're sure of a quantum particle's energy, the less you're sure of its time. I'm not sure what that means. And the more you're sure of its time, the less you're sure of its energy. That is the uncertainty inequality relationship in general. You can just search up ChatGPT, what is the uncertainty principle? How can I use it? What is the difference between the energy time and the position momentum uncertainty principle? Take a look at that. We have an h bar over 2. And you can see it's super similar. They're actually right next to each other. Here we have delta x, delta p subscript x greater than or equal to h bar over 2. Delta e, delta t greater than or equal h bar over 2. Nice. So we did everything here, guys. I'm going to leave this video as is because I don't want to make it too long. I hope this was helpful, and I urge you guys to do this on your own. Do it early before the exam starts. Do it right now, even if you have a couple weeks left to prepare for the exam. Try to figure out what you don't know, and then do the same process again